Welcome back to the Veterinary Epidemiology Series. This module is Applied Biostatistics 1, and it's honestly one of the most exam-relevant modules in the whole series. Today, we're going to demystify the statistics that show up everywhere in veterinary research and all over your ACVPM and NAVLE boards. We'll walk through hypothesis testing, p-values, confidence intervals, t-tests, and ANOVA. Now, I know the word biostatistics can make people want to close the tab, but stick with me here. By the end of this module, you'll be able to pick up a research paper, understand exactly what the numbers are telling you, and spot when a study is being interpreted the wrong way. So let's dive in. Let's start with the big picture because everything else today flows out of this one idea. In research, we almost never get to measure an entire population. Instead, we take a sample, just a handful of animals, and we use that sample to make an educated guess about the whole population. That, in a nutshell, is statistical inference. And we've got two main tools for the job. Confidence intervals give us a range of plausible values for the truth. And hypothesis tests, with their p-values, tell us how much evidence we have against a specific claim. Here's the key thing to hold on to. Both tools come from the exact same place, the sampling distribution of the statistic. And one more rule worth tattooing on your brain. Never interpret a statistic without first knowing how the sample was actually selected. Now let's talk about the two ideas that make classical statistics tick: the normal distribution and the standard error. The normal distribution is that classic bell curve, symmetric and fully described by just its mean and its spread. Here's where people get tripped up, so listen closely. Standard deviation and standard error are not the same thing. Standard deviation describes how much individual animals vary from each other. Standard error describes how precisely we pin down the average. Take our Holstein cows. Individual milk yields vary by about 4.2 kilograms, but with 100 cows, our estimate of the mean is precise to within about half a kilogram. And the magic ingredient here is the central limit theorem, which tells us that with a big enough sample, our sample means follow a normal curve even when the raw data don't. That's the foundation everything else today is built on. Hypothesis testing can feel intimidating, but it's really just a 5-step recipe, and once you know the steps, it's the same every single time. Step 1, state your hypotheses, the null, and the alternative. Step 2, pick your significance level, your alpha, and crucially, pick it before you collect any data, never after, because choosing it afterward is p-hacking. Step 3, calculate your test statistic. Step 4, find your p-value. And step 5, make your decision. If p is below alpha, you reject the null and call it statistically significant. If it's not, you fail to reject. And notice I said fail to reject, never accept. Absence of evidence is not evidence of absence. And here's the rule the boards absolutely love. A p-value is not the probability that the null is true. It's the probability of seeing data this extreme or more so if the null were actually true. Let that distinction really sink in. Whenever we make a decision from data, we can be wrong in two different ways, and this 2x2 table lays them out cleanly. A type 1 error is a false positive. We conclude the BVDV vaccine works when it really doesn't. When we set alpha at 0.05, we're agreeing to accept a 5% false positive rate over the long run. A type 2 error is a false negative. We conclude the vaccine doesn't work when it actually does. And power, which is 1 minus beta, is our ability to correctly catch a real effect when it's there. Now here's the part that makes this really click for vets. This is exactly like diagnostic testing. A type 1 error is a false positive test. A type 2 error is a false negative. And power, is sensitivity. That analogy is one of the highest yield connections on the entire board exam, so make it your own. Confidence intervals are honestly my favorite tool in all of statistics, and here's why. A 95% confidence interval gives you a whole range of plausible values for the truth, and it tells you two things at once: whether a result is significant and how big the effect actually is. Now, the interpretation is subtle, so let's be precise. 95% confidence means the method works 95% of the time, not that there's a 95% chance the truth sits inside this one particular interval. The formula is just your estimate plus or minus about 2 standard errors. Take our Angus cows with a body condition score of 3.2. We're 95% confident the true mean lies between 3.10 and 3.30. Bigger samples give you tighter, more precise intervals. And the takeaway: always report a confidence interval alongside your estimate because it's far more informative than a p-value on its own. Now we get to the workhorses of comparing averages, the t-tests. There are 3 flavors, and the whole game is just knowing which one to reach for. The one sample t-test compares your group's mean against a fixed benchmark, like checking your herd's milk yield against an industry standard. The 2 sample independent t-test compares 2 separate groups, say Angus calves versus Simmental calves. And the paired t-test is for when the same animal gives you 2 measurements, like body condition before and after a feeding change. That pairing is powerful because each animal acts as its own control, which strips out a lot of the noise. One quick technical note: we use the t-distribution rather than z because we're estimating the spread from the sample itself. So remember the cheat sheet: 1 sample for a benchmark, 2 sample for different groups, and paired for the same animals measured twice. So what happens when you've got 3 or more groups to compare? You might be tempted to just run a bunch of separate t-tests, but please don't, and here's why. Every test you run carries its own false positive risk, and with 3 tests, that risk balloons from 5% up to about 14%. ANOVA solves this elegantly by running a single omnibus test that protects your overall error rate. And the idea behind it is beautifully simple. It compares the variation between the groups to the variation within the groups. If the between-group variation is much larger, you get a big F statistics, and you conclude the groups really do differ. But here's the catch you have to remember. ANOVA only tells you that some groups differ, not which ones. So you always follow a significant ANOVA with post-hoc test, and Tukey's HSD is your go-to default. Report the F statistic, the p-value, and then your adjusted post-hoc results. Up to now, we've been comparing averages, but what about counts and categories like vaccinated versus not or sick versus healthy? That's where the chi-square comes in. It tests whether 2 categorical variables are independent of each other, and it's the bread and butter of 2x2 tables in epidemiology. But there's one assumption you simply cannot skip. Every expected cell count needs to be at least 5. If any cell falls below that, chi-square starts to break down and you switch to the Fisher exact test, which is always valid even with tiny samples. In our example here, vaccination status and BRD turn out to be significantly associated with a p-value of 0.002. And one more for the boards. When your data are paired, like the same animal tested twice, you reach for the McNamara test instead. So Fisher for small cell counts, McNamara for paired data. Lock those 2 in, and you're in great shape. Here's a question that comes up constantly in practice. What do you do when your data just don't follow a nice normal bell curve? That's the parametric versus non-parametric decision. Parametric tests, your t-tests and ANOVA, assume normality, and when that assumption holds, they're the most powerful option you've got. But when your data are skewed or they're ordinal like body condition or pain scores, or your sample is simply small, you switch over to non-parametric tests. And the nice thing is there's a direct swap for almost everything. The two-sample t-test becomes Mann-Whitney-U. One-way ANOVA becomes Kruskal-Wallis. Pearson correlation becomes Spearman. The exam rule is simple. The exam rule is simple ordinal data or clearly non-normal data with a small sample means go non-parametric, but for large samples with a continuous outcome, the central limit theorem has your back and parametric tests stay perfectly robust. This slide is one I really want you to slow down for because misinterpreting p-values is probably the single most common mistake in all of science. So let's nail it once and for all. A p-value is the probability of seeing data this extreme if the null hypothesis were true. Full stop. It is not the probability that the null is true, it is not the chance your result was just a fluke, and it is not the probability that your research hypothesis is correct. Now here's the practical wisdom. Statistical significance is not the same thing as clinical importance. Picture 10,000 dairy cows where milking 3 times a day instead of 2 comes out highly significant, p equals 0.0001, but the actual benefit is 50 grams of milk a day. Statistically real? Practically meaningless. With a big enough sample, almost anything becomes significant. So always pair your p-value with an effect size and a confidence interval and let the clinical judgment follow from there. All right, let's put it all together with some worked examples because test selection is exactly what the boards love to probe. Example 1, milk yield before and after a feed additive in the same cows. That's paired data, so paired t-test. And if it's badly skewed, you fall back to Will Coxon. Example 2, BRD across 3 housing types. Those are counts in a contingency table, so chi-square, dropping to Fisher exact if any expected cell is under 5. Example 3, body condition scores with only 15 per group, ordinal plus a small sample, so Mann-Whitney-U. Example 4, somatic cell counts across 4 protocols, a large sample but right skewed, so log transform it and run ANOVA with Tukey. And example 5, lesion score versus vacuum level and ordinal association, so Spearman rank correlation. See the pattern? Ask yourself what kind of outcome you have, how many groups, and whether the assumptions hold. And the right test almost picks itself. Let's bring it home with a quick recap of your statistical toolkit. 1. Statistical inference, using sample data to draw conclusions about a whole population, with confidence intervals and p-values as your 2 core tools. 2. Type 1 and type 2 errors, false positives and false negatives, and remember power equals sensitivity. 3. T-test for 1 or 2 groups, and ANOVA for 3 or more, always followed by post hoc tests like Tukey. 4. Chi-square and Fisher exact for categorical data, with McNamara for paired proportions. And 5. The big one. P-values measure evidence against the null. They are not the probability that the null is true, and statistical significance is never the same as clinical importance. Master those 5 ideas, and the board questions are going to feel a lot friendlier. Thanks so much for watching. Don't forget to like and subscribe, and I'll see you in the next module where we tackle regression and logistic regression. I'll see you there.